Hello everyone. In the previous class we discussed about unique factorization domain and we discussed certain results on unique factorization domain. And today we are going to continue the discussion with factorization in the ring of Gaussian integers Z of I. Z of I is the collection of all elements of the form A plus IB where A and B are integers. And we knew that we have proved Z of I is a Euclidean domain, and we have proved a result which says every Euclidean domain is a principal ideal domain, and also we have proved in the previous class that every principal ideal domain is a unique factorization domain. Therefore, your Z of I is a unique factorization domain. That means every element of Z of I can be expressed as product of finitely many irreducibles, and it is unique up to associates. And further we have defined a Euclidean function d from Z of I to Z defined by d of z equal to a square plus b square whenever z is of the form a plus ib, which is same as n of z. And we know that units of Z of I are plus or minus 1 and plus or minus I, and also z is a unit of Z of I provided n of z is equal to 1. And n of z is always positive whenever z is non-zero. And if n of z is a prime number, then z is a Gaussian prime. That is, z is a prime element in Z of I. We discussed all these results in the previous class. And we know that in a unique factorization domain, prime elements and irreducible elements are identical. Therefore, in Z of I, prime elements and irreducible elements are same. Suppose if z can be factored into z1 and z2, then n of z equal to n of z1 into n of z1 into n of z2, because this is of the form n of alpha equal alpha beta, which is equal to n of alpha into n of beta. We knew this result in the previous classes. We have discussed this. Since n of z is a prime number in z, this is capital Z, that is set of integers, then this product has to be a prime element. Let us assume it is equal to p. So product of these two is equal to p. It is possible only if n of z1 equal to 1 or n of z equal to 1. If this is equal to 1, then this has to be a p. If this is equal to 1, then it has to be a p. So your n of z1 can have either 1 or p. Similarly, n of z2 may be 1 or p depending on z1. If n of z1 equal to 1, we knew from this result, then that element has to be a unit in Z of I. Therefore, if this is equal to 1, then z1 is a unit in Z of I. If this is equal to 1, then z2 is a unit in Z of I. Now, let us consider pi is a Gaussian prime. We knew that we have proved a result. An element is a prime element if and only if the principal ideal generated by that element is a prime ideal of Z of I. And P is Gaussian prime, hence it is non-zero and non-unit. Therefore, this principal ideal pi is a non-zero prime ideal of Z of I. And further you should note that suppose if this mapping is say some j, then if j is a mapping from Z to Z of I, then its inverse, we knew that this is a prime ideal in Z of I. Therefore, its inverse is also an ideal in Z, because we knew the result which says that inverse image of an ideal is ideal. By that, this is an ideal in Z, and Z is also an ideal. Therefore, in fact, the inverse of this is the intersection of principal ideal pi with Z. Further, this ideal is non-zero because pi into pi bar belongs to intersection of these two, and pi into pi bar is a non-zero integer, and thus intersection of these two equal to some principal ideal p, where p is a prime number, because the inverse image of a prime ideal is prime ideal. So this has to be a prime ideal. Therefore, this is a principal ideal generated by p, where p is a prime number. And p, the smallest ideal which contains p, is principal ideal p. Therefore, these two are equal. Therefore, p belongs to this The P belongs to intersection means P must be in both of them. So P belongs to principal ideal pi, but every element of pi is pi into some number. So P is equal to pi into some number. But by divisibility property, this says that pi divides P. So your pi is dividing P. And you should note that P is a prime element and pi is a Gaussian prime. Now since Z of I is a unique factorization domain, any prime element Z of I can be expressed as a product of finite number of primes. And since your pi is Gaussian prime, as pi divides P, pi is one of the factors of P in the factorization of P in Z of I. Thus, by factorizing all primes in Z of I, we obtain all the Gaussian primes. Note that the following are not primes in Z of I because 2 can be expressed as sum of squares of integers. And this is nothing but 1 plus I into 1 minus I, where these two are primes. But 2 is prime in Z. These two are prime in Z of I. And 5, 1 plus 2I into 1 minus 2I, 13 can be expressed this. And hence an element P is prime in Z of I if it is congruent to 3 mod 4. For example, 2 is not congruent to 3 mod 4. Therefore, 2 is not prime in Z of I. But 3 is congruent to 3 mod 4. 3 minus 3 is 0, which is divisible by 4. Therefore, 3 is congruent to this. Therefore, 3 cannot be expressed as sums of squares. 7 is congruent to 3 mod 4 because 7 minus 3 is 4, which is divisible by 4. But 7 cannot be expressed in this way. So any number which is sums of square cannot be congruent to 3 mod 4. Now we knew that our pi divides P. So P must be equal to pi into some number. Let's say P equal to pi into pi dash. Then what is your n of P? Our n of P by definition of n of a plus ib, our n of a plus ib is a square plus b square. By that definition it is p square. And we knew that P, we have written this one as pi into pi dash, but n of alpha into beta is n of alpha into n of beta. By that definition, this is n of pi into n of pi dash. And we are saying product of these two is equal to p square. Then n of pi must be equal to p or p square. It cannot, our n of pi cannot be equal to plus or minus 1. In fact, it cannot be 1 because n of pi is always greater than 0 whenever this pi is non-zero. Therefore, why it cannot be equal to 1? What happens if this is equal to 1? If this is equal to 1, then pi becomes a unit element, which is not true because pi is a Gaussian prime. It is non-unit. Hence, our n of pi must be equal to p or p square. Suppose n of pi is equal to p square. Then what happens? If this is p square, then this should be 1. 1 into p square is 1. So your pi dash becomes a unit. If pi dash equal to unit, we know that we have written p as pi into pi dash. So p equal to pi into pi dash means where pi dash is a unit, therefore p and pi has to be associates by the result which we know that a and b are associates if and only if a equal to b into u, where u is a unit. So similarly, p is equal to pi into pi dash where pi dash is a unit. Because of that reason, pi and p are associates. So associate means since pi is a Gaussian prime, p has to be a Gaussian prime. So p is a Gaussian prime. And what are the units of Z of I? They are plus or minus 1 and plus or minus I. We knew that if a equal to b into u and b is u is a unit, then a and b are associates. In other words, a divided by b is equal to unit implies that a and b are associates. By that result, p and pi are associates if p divided by pi is equal to plus or minus 1 or p divided by pi is equal to plus or minus I, where plus or minus I and plus or minus 1 are units. If you cross multiply, you will get p equal to plus or minus pi or p equal to plus or minus pi I. That means p itself is a Gaussian prime because your pi is Gaussian prime. So p is a Gaussian prime. Itself is a Gaussian prime whenever n of pi equal to p square. Similarly, when n of pi equal to p, If this is P, then it has to be P. So P into P will give you P square. So if n of pi equal to P, n of pi dash is also equal to P. That means we are getting pi and pi dash are Gaussian primes. So that your n of pi into n of pi dash gives you P square. So in the second case, we have split our P into pi and pi dash, where both are Gaussian primes. So if n of pi equal to P square, then P itself is a Gaussian prime. And if n of pi equal to P, then P splits into two Gaussian prime. For this, the examples are given. 2 is a prime. 2 is a prime. So that 2 splits into Gaussian primes 1 plus I into 1 minus I. That's what. Now, also we should note that n of pi equal to P if and only if P is a sum of two squares of integers. That is, if P is of the form a square plus b square, then P can be written as a plus ib into a minus ib, where a plus ib and a minus b are Gaussian primes. That is what 2 can be written as 1 square plus 1 square, which is 1 plus I into 1 minus I, where 1 plus I and 1 minus I are Gaussian prime. Further, P is a sum of two squares if and only if P must be of the form 2 or P congruent to 1 mod 4. Why? What happens if P is congruent to 3 mod 4? Suppose if P equal to a square plus b square, then a square, b square are congruent to 0, 1 mod 4. Then a square plus b square will be either congruent to 0 mod 4 or congruent to 1 mod 4 or congruent to 2 mod 4. A square congruent to 0 mod 4, b square congruent to 0 mod 4 gives you a square plus b square congruent to 0. A square 0, b square 1 gives you a square plus b square is 1. A square 1, b square 1 gives you a square plus b square congruent to 2 mod 4. So a square plus b square will never be congruent to 3 mod 4. Hence, P is equal to a square plus b square whenever P equal to 2 or P is congruent to 1 mod 4. Now we are having a theorem. If P is a prime number and P congruent to 1 mod 4, then P is sum of two squares of integers. Let's prove this one. They are given P is a prime number. Then ZP is a residue class modulo P. What is ZP? ZP is equal to collection of all elements of the form 0 bar, 1 bar, 2 bar, etc. up to P minus 1 bar. And in fact, since P is a prime number, ZP is a field. ZP is a field means it is a abelian group under addition, and non-zero elements of ZP forms a multiplicative abelian group of order P minus 1. And in fact, it is cyclic. It is cyclic, and further, since P is congruent to 1 mod 4, 4 must divide P minus 1 by the definition of congruence. But the order of ZP star is P minus 1. Therefore, 4 divides order of ZP star. But by Lagrange's theorem of finite groups, order of subgroup must divide order of the group. So, order of H must divide order of ZP star. But since this is a cyclic group, the order of the subgroup is same as order of an element. So there has to be an element in ZP star which is of order 4. Let us assume that element is A bar. So order of A bar is 4. Then order of A bar square should be equal to 2. In fact, this is 2, not 4. So that your order of A bar will become 4. Order of A square should be equal to 2. But there is an element whose order is 2. That element is minus 1. Because minus 1 square becomes 1. 1 is congruent to 1 mod 4. So, and further you should note that 1 bar is not equal to minus 1 bar. If 1 bar equal to minus 1 bar, then this becomes 2 congruent to 1 mod 4, which is not true, because P is not equal to 2 here. So P is not equal to 2 because of that reason. And further we should note that ZP star has a unique subgroup of order 2. Therefore, we must have, there is only one subgroup which is having order 2. And since this is cyclic, and order of A bar square is also 2, and order of this is also 2, and order of that subgroup must be equal to order of these two. That means our subgroup will be generated by A bar square, which is same as minus 1 bar. That means A bar square must be equal to minus 1 bar because it is unique. But this implies that A square is congruent to, in fact this is minus 1 not plus 1. Because of this, A square is congruent to minus 1 mod P. That implies that P divides A square plus 1. But that is equal to A plus I into A minus I. You can factor this one in Z of I, that A plus I into A minus I. But you should remember our P is a prime number. Our P is a prime number. If P is a prime number, then P has to divide one of them. Now the question is your P is a Gaussian prime? But you should note that suppose if P divides A plus I, then P will also divide A minus I and vice versa. Thus, P divides both A plus I and A minus I. So both A plus I and A minus I are divisible by P, and there is a result which says if A divides B and A divides C, then A has to divide B minus C. By that result, P divides A plus I minus A minus I, which is equal to 2I. So that implies that P must divide 2I. But this is not possible because P is not equal to 2 and P is congruent to 1 mod 4. Therefore, P cannot be a Gaussian prime. P cannot be a Gaussian prime. Therefore, P is irreducible. Because if it is a Gaussian prime, it is irreducible. But this is not. Gaussian prime means it is not irreducible. Therefore, it is reducible. Let us assume P is equal to A plus IB into C plus ID in Z of I. And both, if one of them are unit, then it becomes irreducible. That's why both has to be non-units. And further, you should note that n of P is nothing but P square, which is equal to n of P is this. So n of P will be equal to n of A plus IB into n of C plus ID. So n of A plus IB into n of C plus ID is equal to P square, implies n of A plus IB must be P, n of C plus ID must also be P. So that their product will be equal to P square. And any of these cannot be equal to 1. Why? Suppose if n of A plus IB equal to 1, then A plus IB becomes a unit, which is not possible. If n of C plus ID equal to 1, then C plus ID must be a unit, which is not possible. That's the reason these two cannot be equal to 1. So if they are not equal to 1, we left out with two options. What is there? This is P and this is also P. It cannot be any of them. If this is 1, then this is P square. But that is not true. If this is P square, then this has to be 1. That is also not true. So we left out with only if this is P, then this also be P. So your n of A plus IB equal to P implies P equal to, we knew that n of A plus IB is A square plus B square, which is the sum of two squares of integers. And this completes the proof. Now corollary, this theorem is due to formats. Prime number P is sum of two squares of integers if and only if P is equal to 2 or P is congruent to 1 mod 4. So the above result gives you P is a sum of two squares of integers whenever P is congruent to 1 mod 4. And above that we are given if P equal to 2, what happens. So combine these two. This gives you the proof of this corollary. And I had given exercise. You just work it out and put it in the assignment. Thank you.